Okay, this is Mr. Jern, and I'm going to talk about AP Physics 1, Workbook 1L, Linearizing Graphs. Linearizing graphs is definitely a skill we're going to be using a lot throughout the year. Um, and so this is just a little practice with that. So our scenario is that Angela, Blake, and Carlos have been given a stopwatch, several large spheres, and a meter stick, and have been asked to determine the acceleration due to gravity. They decide that they need to collect drop height and time for fall, um, or time to fall for the ball at several different heights to create a position versus time graph. Pretty standard stuff. The averages of the collected data are shown in the data table below. So on the unfinished workbook page, this is what you've got, the part in black. And so they have different heights in meters, and you notice they put the units at the top of the column in the header, not for each value in each cell, and the time in seconds. All right, and they did the best they could. They probably got this is probably average. Oh, it says the averages. The averages of the collected data are shown below. So, part A, graph the drop height as a function of fall time on the axis above. So your graph should look a little bit like this. Now, the thing I really like about this is that the data is not perfect. It's experimentally gotten data. It's experimentally determined. And so when you get this, you see this pattern. Now, what you might, this is very common, is sometimes we think, well, we try to force a straight line, but as soon as you try to draw a straight line here, you're going to see the problem with that. It's not a straight line at all. So it has a slight curve upward, so keep an eye out for that. I mean, when you see acceleration, position time, it's going to be an acceleration. It's going to be a curved line. But what I really like about this is the best fit, the trend line, does not go perfectly through all the dots. And this is actually more realistic for when you get experimental data. It's just not going to line up perfectly, and that's okay. Okay, but what this really highlights is don't connect the dots. Okay, do not connect the dots. And I'm writing and it's not quite updating for some reason. That's okay though. Give it a moment and it'll probably update. So do not connect the dots. I'm not sure why it's not, but that's okay. So I'm saying it right here. Don't connect those dots. Draw the best fit trend line. What makes sense? All right. Part B. Based on your graph and the data table at the right, identify the table at the right, identify the correct relationship between the drop height and the time to fall to the ground. This table right here, I think, is invaluable. You should probably have a copy of it handy, either at the beginning of your planner or in your lab notebook or something. Probably the lab notebook would be the best place for it. That seems like it might make the most sense. But anywhere that works for you. These are the different relationships between variables and what you do with them. So if you have a nice diagonal straight line, it's pretty easy. It's a directly proportional relationship. You could just very quickly get the y equals mx plus b graph, and go from there. It's fine. For the rest of them, when you get a curved relationship, this is what you got to do. And just gotta see something really quick. Yeah. Basically, I'll do my best here then, just without the syncing. I apologize here. As x increases, y decreases. X is inversely proportional to y. So what you basically, oh, there we go. So what you have to do there, inversely proportional, means that, so in this one, y is proportional to x. In the next one, basically y is proportional to the inverse of x. So what you got to do for all your x values is take the inverse of it, and you make a new column, and you graph the inverse of x to go along with y. When you get this third kind of graph, y is proportional to the square of x, so you have to make a new column where you square the x's, and then you graph y versus the square of x. And then the final one, the square of y is proportional to the x. Now there's two ways to go about this. And you could say y, the square root of y is proportional to x. In that case, you actually can take the square root of y's and make a new column with them and then graph them along with the x's. Or you can take y is proportional to, I did that backwards. Wow. The square of y is proportional to x. So forget I said that. It's the square of y is proportional to x. And the other way to do that is take the square root of x and make a new column there. I apologize about that, but yeah, it's the same idea. And it honestly, whatever you choose, whichever works. Typically, I would recommend choosing based on the units. Okay, if you have a unit of in the x's of, like, for example, seconds, what's the square root of a second, right? And so it kind of just you just decide which one's going to work better. So I don't know if I would do that. I would probably square the y values instead of having to take the square root of the seconds. It just doesn't make a lot of sense to me. But whatever works is what I would choose. Now, in this case, we have upward curving graph. And so based on the graph and the data table at the right, identify the correct relationship between the drop height and the time. So in this case, we have the third one. So y is proportional to the square of x. And so because y, the displacement or the y value, is proportional to the square of time, the x value. All right, so that's our relationship, and then we go from there. So part C says the relationship between drop height and time to fall can be compared to the equation for a line so that the students can create what is called a linearized graph. Fill in the third column on the data table with the appropriate values and graph to create a linearized line. So now we're going to fill in this third column. And so we do that. We square all the times, and these are our values for that. The units for time squared, believe it or not, is time squared. So it might not make sense right away, but that's okay. Just go with the math, follow the math, okay, and make sense of it all later. It does make more sense the more you do this. So we do this just like that, okay? And I'm going to come back to this in a moment, I believe. Okay, later on we're going to graph that. Now, what is going on with this? This, as it's presented, can be a little bit confusing. I'm going to put it this way. I'm going to start with y equals mx plus b as our slope-intercept formula, and realize, okay, in this case, height is graphed on the y-axis. Okay, that's going to be our changing position in the vertical, our changing vertical position. And okay, there we go. Our slope is going to be the slope of whatever it is. And so what happens is we don't know what it is. X values are time squared. So this is our x's plus b. So I'll put the b there just to kind of complete the formula here. So this x becomes time squared. Remember, x is a mathematical variable. It can represent whatever it represents. It represents. In this case, the x represents time squared. Okay. It's a little confusing because it is not x squared. The x in our linearized equation is time squared. Okay. I'm just going to write that out one more time, like just to kind of. In fact, I'm going to write it in red. X is time squared. All right. So just, it is not x squared. It is, okay, I'm going to leave it at that because it can be a little confusing, but this is the mathematical relationship here. So the height will be equal to whatever the slope is going to end up being times our x value, which is time squared, plus the intercept. Backside. What quantities should be plotted on the graph if the graph is to have a linear trend and the slope of the best fit line is to be used to determine the acceleration due to gravity? So hopefully by now you know what this is. Drop height versus time squared. Okay. Um, and I would do that. Also acceptable is the square root of the dropped height versus time and there's other ways to do it. Now, I don't know why you would choose the square root of drop height, because then you're going to be dealing with the square root of a meter, and that just kind of makes things a little bit awkward. I mean, what is the square root of a meter? I don't know. It mathematically will work out the same, but you're kind of making it a little bit weird for yourself. So I think it's easier to square a unit. It also kind of doesn't make sense, but it makes a little bit more sense than a square root of a unit. So that's up to you. Okay, then it says if the graph drop height versus time squared, the slope will be equal to 1/2 the acceleration due to gravity. If the student graph the square root versus time, the slope will be equal to the square root of half the acceleration due to gravity. All right. So so basically now we plot the points. And once again, the data doesn't exactly line up, and that's great. I love that because it's experimentally gained. And then we had to do something. So do not connect the dots, just draw your best fit line. Okay. Then use the best fit line to find our slope. Do not use your data. All right. And when you find the slope, you're going to find that, again, when you find slope, make sure you show the calculation and don't just put the answer down there. So slope is going to be the change in y over the change in x. You plug in whatever numbers you need to plug in, and then you get 5 meters per second squared. That slope is going to be 1/2 of gravity, 1/2 of g, which if we haven't talked about it, we will talk about that at some point. And so that ends up being g is about 10 meters per second squared. Okay, now that last part we'll talk about another time. Right now we're just talking about the relationship and linearizing the data to get that number.